Schizophrenia. You've heard the word, but what's really going on inside the brain? I mean, how does it all happen, step by step? Well, that's exactly what we're going to do here. We're going to build a visual map, a complete walkthrough of the pathophysiology, from the very first risk factor all the way to the symptoms you see. Think of this as your guide to really visualizing the journey of this illness through the brain. So, to really get this, we've got to go way back to the beginning, 1911 to be exact. The guy who came up with the name, Eugene Bleuer, he wasn't talking about a split personality. No, he meant something much deeper. A split between your thoughts and your emotions. Think about it. What if you heard tragic news but felt an urge to laugh? Not because you're cruel, but because the wiring in your brain that connects sad thought to sad feeling is just scrambled. That's the core idea we're going to build on, this fundamental disconnect. All right, so here's our game plan. We'll start with the roots of risk, then look at the actual physical changes in the brain. From there, we'll zoom in on the scrambled brain signals. And finally, we'll tie it all together to see how this shows up as behavior. Let's get started. Okay, so section 1, the roots of risk. You know, the story of schizophrenia doesn't start when symptoms appear. Nope, it starts way, way earlier, with this complex dance between our genes and the world around us. Just look at these numbers. They really paint a picture. If you're an identical twin and your twin has schizophrenia, your risk jumps to a massive 30 to 50%. I mean, compare that to the 1% risk for everybody else. That's huge. It tells us genes play a major role. But, and this is the really crucial part, it's not 100%, not even close. So what does that mean? It means your genes can load the gun, for sure, but they don't necessarily pull the trigger. So what does pull the trigger? Well, that's where the environment comes in. We're talking about things that happen even before birth, like an infection or poor nutrition during pregnancy, or maybe complications during birth, like a lack of oxygen. Even something like growing up in a really dense urban environment can play a role. These things aren't just random life events. They are the potential triggers that can interact with those vulnerable genes and start to alter how the brain develops. Okay, so we've got our risk factors, the genes and the environment. But what do they actually do to the brain? This is where it gets really interesting, because we don't have to guess anymore. We can literally look inside and see the physical changes. And wow, take a look at this. The difference is just stark. On the left, you have the brain of someone with schizophrenia. On the right, a healthy brain. See those big, dark spaces on the left? Those are the ventricles, and they're way bigger than they should be. And look at the hippocampus. The part of the brain responsible for memory, it's actually smaller. It has shrunk. This is so important to understand. We're not just talking about some abstract chemical issue here. We're talking about real, measurable, physical changes to the structure of the brain. Let's break down exactly what's changing. We see those bigger ventricles, the widening grooves on the brain's surface. But check this out, a smaller thalamus. The thalamus is like the grand central station of your brain. It directs all the incoming sensory information. So if that hub is smaller and not working right, what happens? It's chaos. It's like an air traffic controller that's sending planes to the wrong runways. Sights, sounds, thoughts, everything gets scrambled and misinterpreted before it even gets where it's supposed to go. And this whole process, it's not something that just happens and stops. It's an active, ongoing thing. This chart is, frankly, pretty scary. It shows that during the teenage years, a time when the brain is supposed to be pruning and getting more efficient, people with schizophrenia are experiencing a much faster loss of gray matter. Now, gray matter is basically your brain's processing power. It's the hardware. It's what lets you think, feel, and make decisions. And in this illness, you can see it's literally being lost at a faster than normal rate. So as that gray matter vanishes from the frontal lobe, something critical happens. The part of your brain that acts like the CEO, the part in charge of planning, problem solving, and focus, it goes quiet. It becomes hypoactive. So when a person needs to concentrate or make a decision, that area that should be buzzing with activity just isn't. It's like the boss is out to lunch, permanently. And that is a direct link to so many of the negative and cognitive symptoms, like a total lack of motivation or the inability to organize your thoughts. Okay, so we've seen the large-scale structural problems. Now let's zoom in. I mean, way in, down to the microscopic level of the brain's chemistry. We need to look at the neurotransmitters, the messengers, to see how the actual signals are getting so messed up. All right, for decades, the big idea was something called the dopamine hypothesis, and it made a lot of sense at the time. The thinking went like this. The first drugs that actually worked for schizophrenia all blocked dopamine receptors. So the problem must be too much dopamine, right? Simple. It was a huge breakthrough, but it turns out the real story is a bit more nuanced than that. And here's the twist. It's not one problem, it's two. It's a tale of two pathways. In the pathway that goes up to your prefrontal cortex, the CEO's office, there's actually not enough dopamine, a dopamine drought. And that's what we think causes those negative symptoms, like emotional flatness and zero motivation. But at the same time, in a deeper, more primitive pathway called the mesolimbic pathway, there's a dopamine flood. It's a total overload, and that is what seems to drive the positive symptoms, the hallucinations and paranoid delusions. But hold on, because dopamine isn't the only chemical in this story. Let's talk about glutamate. Glutamate is basically the brain's main go signal. It's the on switch for pretty much everything. The new thinking is that in schizophrenia, this on switch is faulty. It's just not getting flipped enough. And here's the crazy part. If you give a healthy person a drug that blocks these glutamate receptors, they can start to show symptoms that look a whole lot like schizophrenia. This has led scientists to think that maybe the whole dopamine mess is actually a downstream effect of a more fundamental problem with glutamate. Okay, we've got all the puzzle pieces on the table now. The genetic risks, the environmental triggers, the physical brain changes, and the scrambled chemistry. Now for the final step, putting it all together to see how this translates into the actual symptoms a person experiences. So clinically, symptoms get sorted into three main buckets. First, you have positive symptoms. Think of these as things added to a person's experience, like hallucinations or delusions. Second, negative symptoms. These are things that are taken away or lost, like motivation, speech, or the ability to feel pleasure. And finally, you have cognitive symptoms. This is the trouble with brain work. Poor memory, disorganized thinking, and a really hard time focusing. And this table, right here, this is our whole visual map all in one place. Let's trace it. You get that underactive prefrontal cortex, the sleepy CEO, starved of dopamine. And what's the result? Bam, negative and cognitive symptoms. Then you have the overactive limbic system, flooded with dopamine. And what does that lead to? Bam, the positive symptoms. And underpinning all of it, you've got that widespread problem with the glutamate on switch. See how it all connects? It's a chain reaction, a cascade, where one thing leads to the next, and the end result is a complete change in how a person perceives and interacts with the world. So we've walked through the biology, we've mapped the entire storm inside the brain, but let's take a step back from this science for just a second. After seeing all of this, seeing how the brain itself physically changes, you have to ask yourself a really profound question. If the hardware is different, if the very organ that creates our consciousness is altered, where does the illness end and the person begin? There's no easy answer to that, but it's a powerful reminder that behind all of this complex pathophysiology, there is always a human being at the center of the story.